Welcome back everyone to the Calc channel. Today we'll be covering a very important topic, the MVT, as well as introducing the EVT and local and global extrema. So all very important concepts. For the mean value theorem, if we have a function f continuous over AB and differentiable over open AB, then the mean value theorem, also written as the MVT, guarantees a point within that open interval where its instantaneous rate of change is equal to the average rate of change over the interval. So here we see AB, these are basically the boundaries of this interval. It has an average rate of change. And what the MVT guarantees is that if you have a differentiable function over AB, then you can find this point between AB. So there exists a C between AB such that f prime of C is equal to the average rate of change, which is equal to f of B minus f of A over B minus A, which is exactly the slope of the secant line that connects AB. This is a very important theorem that is directly tested in many of the FRQ questions. So for example, here we have f of t denotes the number of gallons per second at a pumping station. And we have, must there exist a value of C such that f prime of C is 0? So we are given that f is a differentiable function, which means definitely for any interval it is differentiable. So and that also implies continuity. So we have differentiable, we have continuity, and that means that we can apply the MVT. So C equals 60 is here, C equals 120 is here. The MVT, so we first say f is differentiable and continuous over 60, 120, let's say. Then MVT guarantees that there exists a C within this such that f prime of C equals f120 minus f of 60 over 120 minus 60. And that is equal to 0.1 minus 0.1 over 60, and that's equal to 0. So in general, for an AP FRQ, it suffices to write the conditions that support that you can use a theorem. So these are the conditions. Write the name of the theorem, and then you write the process that supports a final answer, which is this. And the same framework we can use for many FRQs. So for example, here, this is actually a little bit more difficult than the previous one, because instead of giving the range, it gives you like a general range, and it asks you to say why there must be at least one time such that this is 2. And usually the way to do this is you find in this interval, you find 2 points that have a secant slope of 2, right? So we identify which ones it could be, and we can see, for example, this would be a valid interval. So we see the h of 5 minus h of 3 over 5 minus 3. This secant slope is equal to 2, right? So we can choose these 2 points, and we can say that the MVT guarantees that there exists a t within 3 and 5 such that h prime of t, oops, let me redo that, h prime of t is equal to 2. And you use the calculation from here. Right, and because t is within 3 and 5, t is within this interval, so it satisfies this. Okay, now we're going to move on to some MCQs. For what value of x does the rate of change of f equal to the rate of change over that interval. So this is like sort of like verifying the MVT. It's not exactly using it. It's sort of taking it for granted and like asking you what x that would be. So we can simply just take the derivative here and solve a quadratic. So this should be equal to the average rate of change over the interval, which is f of 5 minus f of 0 over 5 minus 0. And that is equal to 125 minus 50 plus 25 over 5. And that is equal to 20. So we get 3x squared minus 4x minus 15 is 0. And so we can just solve this quadratic right over here. And that is minus 3 plus 5 equal to 0. So x is equal to 3 because we want x to be within this interval. Okay, this shows a differentiable graph. Which of the following would be the x-coordinate of a point at which the line tangent to this? So this is like just a visual estimation. So we have a secant here. So this is 1, this is 5, and it has a slope, right? So this is the secant line through the points this and this. This is the secant line. And we want to find the x of a point in this interval where the slope is equal to this secant. And so that would be something, well, we just check each of them. We draw an approximation. This is clearly not true. This is clearly too big. This seems just about right. This is negative, literally. So we can say this is a fairly good estimate, or like a fairly good parallel to the secant line. So we can just take point U. Here we have, if C satisfies the conclusion for derivatives of this, then C would be what? Okay, well, that if it satisfies the conclusion for the MVT, it basically is that point where the average derivative is achieved. So basically it's telling us that f prime of C is equal to f of pi minus f of 0 over pi minus 0. And that is equal to 0 minus 0 over pi. That's just 0. So we want the point on a sine graph where the derivative equals 0. So then the derivative of f is just 2 cosine x, and that must be equal to 0 for C. So we can just solve this, and cosine x equals 0 and x equals pi over 2. So it's B. So now we have a couple more exercises for you. This one we already covered. This one's somehow redundant. But the others are extra practice for you. So you can just take a look here. All right. Next we have the concepts of local extrema. Basically, a function f has a local extremum if it's basically the maximum or the minimum in its neighborhood. So we say that a local maximum at x equals c exists if within an interval ab, f of c is greater or equal to every x in a to b. And so that is what we call a local maximum for ab. And you can do the same definition for minimum. This is all very intuitive, right? So if this particular c is greater than everyone else from a to b, like this, or it's smaller than, then we call this a local maximum, and we call this a local minimum. Right, and the notion of a local extremum relies on the concept of a neighborhood. So right now we define this for a to b, but then as long as there exists some open interval ab around c where this is true, then we can call this a local extremum. So for example, if we have something like this, something here, where you only have a very brief peak, this would still be considered a local maximum because we can still find some neighborhood around it that has it as a local extremum. So here we would have two local extrema, one local max, one local min. Then we have global extrema. This one's even easier to understand. So like if you have a function, let's say it goes like this and it goes like this, then we call this point up here the global maximum of the function, because its value is greater than every other point on the function. So if we have f of c is greater or equal to x for all x in the domain of f, so every x in the domain of f is less than or equal to c, then f of c is the global maximum. We can define global minimum very similarly. So if you have a value, or if you have an x that has a value less than or equal to everyone else's, then that is a global minimum. And we have a property that if you have a global extremum, you must also have that point as a local extremum. And that is very simple, because if you're greater or equal to everyone in the function, or less than or equal to everyone in the function, then you must be greater or equal to or less than or equal to everyone in your neighborhood, right? The neighborhood is a subset of the total or the global domain. Now, another thing that I want to note is endpoints. So if you have an endpoint that looks like this would still be considered a local maximum endpoint. So you need to check basically at this point if this right-hand side is increasing or decreasing. And it's possible that this endpoint can be a global extremum. So for example, if our function is only defined like this, then this is a global maximum as well. Right, basically what the EVT guarantees is that if you have an interval AB, then you must have a minimum value and a maximum value. And this is guaranteed only if f is continuous. This is very important. So if you think about it intuitively, if you want to go from A to B, you have one stroke, and you would definitely have a minimum and a maximum. And this is one intuition for this, is that because it's continuous, you're basically constantly the set of values you cover is always like a minimum to a maximum. And like if you go more down, you're expanding this minimum downwards, and if you're going up, you're expanding this maximum upwards. So it's always this one interval. And so here, for example, we see this this holding true. So for example, over AB here, this is the global max, this is the global min, this is the global max, this is the global min. But of course, it doesn't necessarily have to be global. Really, it's more of a local idea. It's not even local. It's maximum, minimum over AB. It wouldn't be local or global. Now, the EVT only guarantees extremum on closed intervals. This is because you could have either extremum on an endpoint, as we see here. In general, though, this is not really tested directly. It's in most cases taken for granted that there exists some extremum over an interval. So just know this. I haven't seen it explicitly tested, though.